Understanding the factors affecting the value of chemical shift, understanding the effect of different electronic effects on the chemical shift value, understanding the effect of hydrogen bonding and solvent effects on the chemical shift value, and also to understand and comprehend the anisotropic effect. Now let us introduce this topic, students. The chemical shift of a given proton is not an invariant property of a molecule like melting point or boiling point, but it will change depending on the molecular environment that is surrounding it. The chemical shift depends on several factors which are in detail described. First, we will take up, students, the electronegativity effects which are affecting the chemical shift value. A proton is said to be deshielded if it is attached to electronegative atoms or electronegative group. Greater is the electronegativity of the atom, greater is the deshielding of that particular proton. Larger is the deshielding of a proton, larger is the chemical shift value. The chemical shift values of CH4, CH3F, CH3Cl, CH3Br and CH3I, that is methane, methyl fluoride, methyl chloride, methyl bromide and methyl iodide protons are 0.33, 4.26, 3.05, 2.68 and 2.16 respectively. Since fluorine is the most electronegative atom and hence the chemical shift of methyl fluoride protons is very high. Whereas if you see for iodine, because it is the least electronegative amongst the halogen series, it shows a lower value of chemical shift than the methyl fluoride. The structures and the ppm values are shown here in the figure. As the number of electronegative atoms or groups attached to a particular carbon containing that proton increases, the chemical shift value also increases because of the increasing deshielding of the concerned proton. The chemical shift values of methane, methyl chloride, dichloromethane and chloroform protons are 0.33, 3.05, 5.28 and 7.23 respectively. Now I hope you shall be able to appreciate as the electronegative chlorine atoms increase, the chemical shift value also increases. The structural variations are shown in this figure. Here, students, a point to note is that the inductive effect weakens with the increasing distance. Therefore, as the distance of proton increases from the electronegative atom or group, the deshielding effect due to it also diminishes away, and hence the farther protons from the electronegative atom show lower value of chemical shift as compared to the closer protons. The chemical shift values of methyl protons in methyl chloride and ethyl chloride are 3.05 and 1.48 respectively. Now this difference of 3.05 and 1.48 is quite appreciable, and you shall be able to understand the distance inductive effect also weakens. Next, students, let us consider the steric effects. In overcrowded molecules, it is possible that some protons may occupy sterically hindered positions resulting in van der Waals repulsion forces. In such molecules, students, the electron cloud of a bulky group, that is the group which is hindering or the hindering group, will tend to repel the electron cloud surrounding the proton. Thus, such a proton will be deshielded and will resonate at slightly higher value of chemical shift than the expected in the absence of this effect. Next, students, we would like you to consider hydrogen bonding as an effect which affects the value of chemical shift. In general, hydrogen bonded protons show higher value of chemical shift than the non-hydrogen bonded protons. Due to the high electronegativity of the atom to which the proton is hydrogen bonded, the electron cloud around the proton is decreased and thus causes deshielding of that particular proton. The downfield shift of the absorption depends on the strength of hydrogen bonding involved. Greater is the degree of hydrogen bonding with that proton, greater will be the downfield shift of that proton. Now this is due to hydrogen bonding that the chemical shifts of OH, NH and SH protons vary over a wide range of chemical shift values. It is unpredictable as the extent of hydrogen bonding depends on concentration, temperature, solvent and the compound structure. The OH signals tends to move downfield at higher compound concentration because of increased hydrogen bonding. Also on increasing the temperature, hydrogen bonding decreases and hence OH signals move slightly upfield. Both OH and NH signals move downfield in hydrogen bonding solvents like DMSO or acetone. The intermolecular and intramolecular hydrogen bonding can be distinguished by the use of proton NMR spectroscopy easily. The intermolecular hydrogen bonding depends on the concentration of the sample and decreases on dilution with the non-polar solvent and also with increasing temperature. As this bonding is between two molecules, not within a molecule. The pure ethanol shows signals near 5 ppm, but on dilution with non-hydrogen bonded solvents like carbon tetrachloride, CdCl3 and deuterated benzene, the OH signal shifts upfield due to the breaking of intermolecular hydrogen bonds. The more acidic hydroxyl group of phenol also shows similar concentration dependence to that of alcohols. The phenolic OH peak at different percent concentrations of phenol in CdCl3, that is deuterated chloroform, are shown and we will discuss it. CH signals are not shown here. Now as you can see, we range from a concentration of 100%, 10%, 5%, 2%, 1% and in CdCl3 solution of phenol. See how the chemical shift varies from 7.45 to 4.35 and in between there are three ranges of the same value of the same compound in CdCl3. Now the intramolecularly hydrogen bonding does not depend on the concentration at all because the hydrogen bonding in this case will be within the same molecule and hence no change in their absorption position on dilution is seen. The salicylates, enols of beta diketones and carboxylic acids are some classical examples of intramolecularly hydrogen bonded compounds. The hydroxyl proton of enol form of 2,4-pentane dione, that is 4-hydroxy pent-3-ene 2-one, shows a peak significantly downfield, that is 10 to 16 ppm compared to the OH signal in other functional groups due to strong intramolecularly hydrogen bonding. Similarly, the hydroxyl proton of carboxylic acid displays a very downfield peak at about 10 to 13 ppm, which may be attributed to the favored hydrogen bonded dimeric association. Now this you can see in the figure and the downfield value caused due to intramolecular hydrogen bonding. Next we come on to the solvent effects. Chloroform, that is deuterated chloroform CdCl3, is the most common solvent for NMR measurements. One thing, because it is cheap, because the deuterated atoms are very less, that is 1 in this solvent. Other deuterium labeled compounds such as deuterium oxide D2O, benzene D6, C6D6, acetone D6, CD3, COCD3 and DMSO D6, that is CD3SO CD3, are also used as NMR solvents. All these solvents vary considerably in their polarities and magnetical susceptibilities. Hence, the NMR spectrum recorded in one solvent may be slightly different from that recorded in the other solvent. Hence, it is important to mention the solvent used whenever we do an NMR experiment. The NMR signals for protons attached to carbon are generally shifted slightly by changing solvent, except where significant bonding or dipole-dipole interaction might arise. The changes in chemical shifts due to solvents change are minor, being on the order of plus minus 0.1 ppm. However, students, in some cases the changes are more. The aromatic solvents benzene and pyridine cause changes in chemical shifts as large as 0.5 to 0.8 ppm compared to less magnetically active solvents like chloroform or acetone. It is observed that the carbonyl groups form weak pi-pi collision complexes with benzene ring that persist long enough to exert a significant shielding influence on nearby groups. The second noteworthy change can be observed in the spectrum of tertiary butanol in DMSO, where the hydroxyl proton is shifted 2.5 ppm downfield from where it is found in dilute chloroform solutions. Why is this happening? This is due to strong hydrogen bonding of the alcohol OH to the sulfoxide oxygen, which not only deshields the hydroxyl proton but secures it from very rapid exchange reactions that prevent the display of spin-spin splitting. Now, similar but weaker hydrogen bonds are formed to the carbonyl oxygen of acetone and the nitrogen of acetonitrile. Next, we come on to shielding and deshielding in aromatic protons. Electron donating substituents cause shielding of the aromatic protons as they increase electron density on the benzene ring. The order of shielding is ortho is greater than para is greater than meta, because the electron density at ortho and para positions are higher due to the plus M effect. On the other hand, the electron withdrawing substituents cause deshielding of all the aromatic protons. The order of deshielding is in the order of ortho greater than para greater than meta, because the electron withdrawing effect is maximum at ortho and para positions due to minus M effect. Anisotropic effect, that is the space effect. In some cases such as alkenes, alkynes, carbonyls and aromatic compounds, the chemical shift cannot be explained only on the basis of the above fact. The carbon atom in acetylene is more electronegative because it is sp hybridized than the carbon atom in ethylene because it is sp2 hybridized. But the chemical shift value of acetylenic protons is less because it is more shielded than the ethylenic protons. Such anomalous behavior can be explained by anisotropic effect produced by circulation of pi electrons under the influence of applied magnetic field. Anisotropy means uneven magnetic field in space. That is, different regions of space are characterized by different magnetic field strengths. The anisotropic effect depends upon the orientation of molecule with respect to the applied field. Now you can see here the ethylenic proton and the proton present in the benzene ring. The ethylenic proton is relatively shielded and has a chemical shift value of 2.5, whereas ethylenic proton is deshielded and has a value of 4.5 to 6 ppm range, and the highest deshielded will be the proton attached to the benzene ring, and that will have a value which varies in the range of 6.5 to 8 ppm. In fact, a proton experiences three different fields: the applied field, the induced magnetic field generated by sigma electrons, and the induced magnetic field generated by pi electrons. The pi electrons are more polarizable than sigma bond electrons. Therefore, the induced magnetic field due to pi electrons movement is stronger, that is strong secondary fields that perturb the nearby nuclei, than that generated by sigma electrons. Now, depending on the position of the proton in the induced magnetic field, it can be either shielded, that is smaller delta value, smaller chemical shift, or deshielded, that is higher chemical shift or higher delta value. Let us now first consider the alkene protons. An alkene molecule in an external magnetic field is so oriented that the plane of the double bond is perpendicular to the applied magnetic field. Thus, the circulation of pi electrons is perpendicular to the carbon-hydrogen framework of the molecule. Now, as a result, the induced magnetic field is caused by the circulation of pi electrons is in the opposite direction of applied magnetic field, that means diamagnetic, around the carbon atoms and in the direction of applied magnetic field, that is paramagnetic, in the region of olefinic protons. Therefore, olefinic protons experience greater field strength and consequently resonate at larger value of chemical shift. Now, this is clearly described in the figure that is shown here. Now, we can consider the alkyne protons. An alkyne molecule, when placed in an external magnetic field, is so oriented that the plane of the triple bond lies parallel to the direction of applied magnetic field. The induced magnetic field caused by the circulation of pi electrons of the triple bond is in the opposite direction of the applied field in the region of acetylenic protons. Therefore, acetylenic protons are shielded and experience lesser field strength and consequently resonate at smaller value of chemical shift or delta. This again is clearly approachable with the figure that you can see here. Let us now come on to another type of pi bonds, that is carbonyl protons. Carbonyl compounds, when placed in an external magnetic field, is so oriented that the plane of the carbon-oxygen double bond is perpendicular to the applied field. The circulation of pi electrons generates an induced magnetic field which is in the direction of applied magnetic field at the aldehydic protons. Therefore, aldehydic protons experience greater field strength. You can call it as the diamagnetic effect, and consequently it resonates at a larger value of chemical shift and causes deshielding. In addition, the high electronegativity of oxygen atom also contributes to the higher delta value of aldehydic protons. This is clearly seen in the figure that you can see. Now, let us come to the pi electrons and their effect on the chemical shift of aromatic protons. In benzene, the pi electrons are delocalized cylindrically over the aromatic ring, that is above and below the plane of the ring. When a magnetic field is applied perpendicular to the plane of the aromatic ring, the circulation of pi electrons produces a ring current which induces a magnetic field perpendicular to the plane of the ring. The induced magnetic field is in the opposite direction. Again, diamagnetic effect, as the applied field at the center of the ring, but outside the ring it is in the same direction, or the paramagnetic effect of the applied field. Therefore, the protons at the periphery of the aromatic ring, that is the aromatic protons, experience magnetic field and resonate at higher delta values. That means we can call it deshielding. Protons which are present above or below the plane of the aromatic ring resonate at lower delta values, and hence these protons can be known as shielded protons. Again, you can see in the figure whatever I have said in the past paragraph, and you can see how the magnetic field is being generated for the aromatic protons and out of the plane of the benzene ring. Now, let us consider the case of methyl benzene. Methyl benzene has two different types of protons. a multiplet near 7 ppm is observed due to aromatic protons. The methyl group CH3 in methyl benzene produces a signal at 2.3 ppm, whereas methyl group attached to the acyclic conjugated alkene, that is in CH3CH double bond CH2, appears at 1.95 ppm. This high value of chemical shift is due to deshielding effect of ring currents, that is cyclic system with delocalized electrons in aromatic compounds compared with the deshielding effect of conjugated alkene groups. A similar effect is observed in 14 annulenes. Now you can observe in this figure that the protons outside the ring are strongly deshielded and produce the signals at 8 ppm, whereas inside the ring protons are strongly shielded and they produce a signal at around minus 1.8 ppm. Now let us consider the case of alkanes. The sigma bonding electrons also produced an anisotropic effect, but it is less pronounced than that produced by circulating pi electrons. The axis of C single bond C bond is the axis of deshielding. The single bond anisotropy can be observed in alkanes of the type RCH3, R2CH2 and tertiary ones R3CH, as well as the equatorial versus axial protons in a fixed cyclohexane ring. The equatorial protons in a conformationally rigid cyclohexane ring appear more downfield by nearly 0.5 ppm than the axial protons on the same carbon. This effect can be explained on the basis of anisotropy effect as shown in the figure, where the equatorial protons reside in the deshielded region of the C single bond C anisotropy and the axial reside in the shielding region, that is minus delta region. The axial and equatorial protons on the C1 are equivalently positioned with respect to the C1-C2 and C1-C6 bonds, and these do not produce any differential effect. However, the C1 axial proton is within the shielding region of the C2, C3 and C5, C6 bonds, whereas C1 equatorial proton is within their deshielding region. An alternative explanation for this can be, or additional contributing effect for this can be, is based on the supposition that the CH bond is stronger sigma donor than a CC bond, which leads to increased electron density in the axial protons anti to 2 CH bonds, hence shielding effect, that is minus delta region. This is clearly seen in the figure that is shown here to you. The methyl protons, that is the CH3 protons, appear near 0.9 ppm. A methylene protons show signal near to 1.2 ppm and a methyne proton, that is a CH proton, shows near 1.7 ppm. The high frequency position of methyne protons, that is in R3CH tertiary ones, compared with methylene protons in secondary alkanes, that is R2CH2, and that with the comparison of methyl protons, that is the primary ones RCH3, may be attributed to the anisotropy of the additional CC bonds. The tertiary proton falls in the deshielding region of 3 C single bond C bonds, secondary protons in the deshielding region of 2 CC bonds, and the primary proton falls in the deshielding region of only 1 CC bond. Now this effect is clearly shown in the figure that you can see here, students. Let us now summarize this module, students. In this module, you have effectively learned that the frequency at which the particular proton comes into resonance is known as its chemical shift, that the tetramethylsilane is used as an internal standard to record an NMR spectrum. Some factors like electronegativity, inductive effect, resonance effect, aromaticity can change the original chemical shift value. Electronegative atoms, groups, withdraw electron density from neighboring groups. This causes the less electron density around the protons, and hence the signal produced by these protons is shifted to downfield values of chemical shift. The chemical shift of a proton is also sensitive to diamagnetic effects that result from the motion of nearby pi electrons. The magnetic field causes the pi electron to circulate, and this flow of electron creates an induced local magnetic field.